Here's a situation most people have lived through. Your internet stops working. Maybe the router needs a restart. Maybe there was a brief outage. Maybe your ISP had a hiccup. Whatever the cause, you fix it. The router comes back up. The connection light turns green, and then nothing. The browser still times out. Things still don't load. For 30 seconds, a minute, sometimes longer, the network acts like the problem hasn't been fixed yet, even though it has. And then gradually, things start working again. First some sites, then others, then everything. What was happening in that window? The physical connection was restored. Power was on. Cables were plugged in. So what exactly was the network waiting for? The answer is that fixing a physical connection is the easy part. The harder part, the part that takes time, is getting every router involved in your traffic to know that the connection is fixed. Update their picture of the network and start making decisions based on the new reality. That process has a name. It's called convergence, and understanding it explains not just why your router takes a minute to recover, but why even the internet's largest outages take the time they do to resolve. To see why convergence takes time at all, we need to think about what routing actually requires. Routers make forwarding decisions based on their routing tables, maps of what destinations are reachable through which paths. And those tables don't come preloaded with knowledge of the entire internet. Routers build them dynamically, by communicating with neighboring routers, sharing information about what they can reach, and computing paths from what they learn. This means that every router's routing table is a model of the network, a snapshot of what that router currently believes to be true. And like any model, it can be out of date. When the network changes, a link goes down, a connection comes back up, a new router is added. The routers closest to that change notice it immediately, but routers further away have no idea anything happened. They're still operating on their old model. Their routing tables reflect the world as it was, not the world as it is. For the whole network to respond correctly to the change, every relevant router's table has to be updated. And because routers learn from each other, passing information from neighbor to neighbor, that update has to travel hop by hop outward from the point of change, until it reaches every router that needs to know. Convergence is the period between when a change happens and when every router's table reflects that change. While convergence is in progress, the network is in a transitional state. Some routers know the new reality. Others are still operating on the old one. Traffic behaves inconsistently. Some packets get through, others don't. Some take longer routes, some hit dead ends. The network isn't broken during convergence. It's catching up. Let's make this concrete with a simple picture. Imagine 5 routers in a chain, A, B, C, D, E, each connected to the next. Router A is at one end, router E at the other. Traffic flows from A through to E regularly. Now the link between C and D fails. C notices immediately. It can no longer reach D directly. C updates its own routing table, marking the path through D as unavailable. But B doesn't know yet. A doesn't know yet. They're still forwarding packets towards C, expecting C to pass them along to D and then E. For a brief moment, those packets arrive at C and go nowhere. C can't deliver them. The path is broken from C's perspective, but A and B don't know that yet. C now sends an update to its neighbors, B in this case, telling it the path through D is gone. B updates its table and sends an update to A. A updates its table. Now all 3 routers know the path is broken. But here's the thing, knowing the path is broken isn't enough. The routers now need to find an alternative path. Maybe there's another route, a backup link somewhere in the network that goes around the broken segment. The routers need to discover that alternative, propagate that information, and update their tables with the new best path. Only when every router along the new path has updated its table, knows the broken route is gone, knows the alternative is available, has computed and installed the new forwarding decision, does traffic start flowing correctly again. That whole process is convergence, from the moment the link failed to the moment every table is correct. And the time it takes depends on several factors. The first factor is how quickly the failure is detected. Routers don't immediately know when a neighboring router or link becomes unavailable. They find out through a combination of physical signals and protocol messages. If a cable is physically disconnected, The router detects the loss of signal on that interface almost instantly, within milliseconds. But if the link is technically up while packets are silently dropped, a misconfigured device or a congested path, the router has no physical signal to detect. It only finds out when it stops hearing from its neighbor. Routers send periodic hello messages to their neighbors, small packets that say essentially, "I'm still here." If a router stops receiving hello messages from a neighbor for a defined period, it declares that neighbor unreachable and removes the routes it learned from it. This detection timer is configurable, and it's one of the most direct levers operators have over convergence speed. A hello interval of 1 second with a dead timer of 3 seconds means failure detection within a few seconds. Many networks use longer timers, 10 or 30 seconds, to avoid false alarms on flaky links that briefly drop hello messages. Longer timers mean slower detection. Slower detection means slower convergence. The second factor is how quickly updates propagate. Once a router detects a change, it sends updates to its neighbors. Those neighbors update their tables. The speed at which this ripple travels across the network determines how quickly every router reaches the new consistent state. In link state protocols like OSPF, used inside most enterprise and ISP networks, updates are flooded immediately to every router in the network at once, rather than passed step by step. A single router's observation of a link failure reaches every other router in seconds. OSPF-based networks typically converge in under 10 seconds, often much faster with tuned timers. In the protocol that governs routing between organizations on the Internet, BGP, updates travel far more slowly by design. BGP deliberately batches updates and rate limits how quickly changes propagate to prevent instability at global scale. BGP convergence can take minutes. During a major internet routing event, some parts of the network converge in 30 seconds, while others take 5 minutes. That uneven convergence is exactly why major outages often show a pattern of gradual recovery. Things come back for some users before others, region by region, provider by provider. The third factor is whether an alternative path exists and how quickly it's found. If the network has only one path between 2 points, convergence after a failure means waiting for the link to be restored. There's nothing to converge to. But if there are redundant paths, which good network design always provides, convergence means finding and installing the best alternative. The time this takes depends on whether the alternative was already known and sitting in the routing table as a backup, or whether routers have to rediscover it from scratch through protocol exchanges. Well-designed networks pre-compute backup paths, so failover is nearly instant. The alternative is already known, and switching to it is just a table update. Less well-designed networks require the full discovery and propagation cycle to find an alternative, which takes longer and produces a wider convergence window. Convergence is not a flaw in routing. It's an inherent consequence of how distributed systems work. No single router has a complete real-time view of the entire network. Knowledge is local. Changes are detected locally, then shared. The sharing takes time. The computation takes time. The installation of new forwarding decisions takes time. Every one of those steps is necessary, and every one of them contributes to the convergence window. What engineers can do is minimize that window through faster detection timers, faster flooding mechanisms, pre-computed backup paths, and careful network design. That reduces the diameter of the area that needs to converge after any single change. Modern networks are dramatically faster to converge than networks from 15 years ago, largely because of improvements in all of these areas. But convergence time never reaches zero. There will always be a window, however brief, between when something changes and when the entire network knows about it. In that window, the network is doing exactly what it's designed to do, not failing, but catching up, carrying traffic as best it can on the information it has, while simultaneously working to update that information as fast as the protocol allows. 30 seconds of partial disruption after your router reboots isn't the network misbehaving, it's the network converging. 1,000 small decisions rippling outward from your router, updating tables, recomputing paths, settling into a new consistent state. By the time your browser loads again, that process is complete. The network has agreed on a new picture of reality. and traffic flows.